Latent heat and changes of state. Recap: specific heat capacity. Before we move into latent heat, let's remind ourselves of something we already know. Specific heat capacity tells us how much energy is needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. When the temperature of an object is changing, we use the equation Q equals mc delta T. However, that equation only works when there is no change of state. There's another way energy can be stored, not in particle motion, but in the bonds between particles. And that's where latent heat comes in. True or false? Temperature. During melting. Let's test your intuition. When a substance is melting, its temperature stays the same even though it is still absorbing heat. Is that true or false? The correct answer is true. During melting or boiling, energy is still being added, but the temperature does not increase. This is one of the most important ideas in thermal physics. Why temperature stays constant? So why doesn't the temperature rise? Temperature depends on average kinetic energy, which is linked to particle speed. During a change of state, the energy being added does not increase particle speed. Instead, the energy is used to break intermolecular bonds. In a solid, particles vibrate in fixed positions. As energy is added, particles gain enough energy to overcome the attractive forces holding them together. They begin to move more freely, but they don't move faster until all bonds are broken. That's why the temperature stays constant during melting and boiling. Introducing latent heat. This brings us to a new concept, latent heat. Latent heat is the energy absorbed or released during a change of state without a temperature change. The word latent means hidden. The energy is hidden because it doesn't show up as a temperature increase. Latent heat explains why ice melts slowly even when heat is added, and why steam at 100 degrees Celsius can cause much worse burns than boiling water at the same temperature. Types of latent heat. There are two main types of latent heat we need to know. The latent heat of fusion is the energy required to change 1 kilogram of a solid into a liquid at its melting point. For example, ice turning into water at 0 degrees Celsius. The latent heat of vaporization is the energy required to change 1 kilogram of a liquid into a gas at its boiling point. For example, water turning into steam at 100 degrees Celsius. The latent heat of vaporization is always much larger than the latent heat of fusion. Heating curve for water. Let's now connect this to the heating curve for water. This graph shows how temperature changes as energy is added. At first, the temperature rises as ice warms up. Then, the temperature stays constant at 0 degrees while the ice melts. Once all the ice has melted, the temperature rises again as liquid water warms up. At 100 degrees, the temperature stays constant again while the water boils and turns into steam. Only after all the water has vaporized does the temperature of the steam increase further. Analyzing the heating curve. We can break the heating curve into 4 stages. First, initial heating. Temperature rises and we use Q equals mc delta T. Second, melting. Temperature stays at 0 degrees and we use Q equals ml sub F. Third, liquid warming. Temperature increases again and we use Q equals mc delta T. Fourth, vaporization. Temperature stays at 100 degrees and we use Q equals ml sub V. Each stage requires a different equation depending on whether temperature is changing or the state is changing, the latent heat equation. During a change of state, we use a new equation, Q equals mL. Here, Q is the energy transferred in joules, m is the mass in kilograms, L is the specific latent heat of the substance. We use L sub F for fusion and L sub V for vaporization. Each substance has its own latent heat values. Solving phase change problems. When solving latent heat problems, follow these steps carefully. First, identify the state change: melting, boiling, freezing, or condensing. Second, choose the correct latent heat value. Third, apply the equation Q equals ml. Always check that the mass is in kilograms. If temperature changes as well, you may need to use both equations in separate steps. Real-world applications. Latent heat plays a major role in the real world. In weather systems, evaporation absorbs latent heat from the oceans, cooling the surface. Condensation in clouds releases that energy, helping drive storms and winds. Sweating cools your body because evaporation absorbs latent heat from your skin. In cooking, steam carries more energy than boiling water due to its high latent heat, allowing food to cook faster. Latent heat application quiz. Let's apply what we've learned. Pause the video here and have a go at these problems. Melting and boiling are the two processes where energy is absorbed without a temperature change. To vaporize 1 kilogram of water at 100 degrees, we multiply the mass by the latent heat of vaporization, giving 2.26 million joules. For multi-step problems, such as melting ice below 0 degrees, we calculate the energy to raise the temperature first, then add the energy required for the phase change. Get creative. Experimental design. Now let's think like physicists. Design an experiment to measure the latent heat of fusion of ice. You would use a calorimeter, thermometer, balance, heater, and ice. You'd carefully measure the energy supplied and the mass melted, then use Q equals ml sub F to calculate the latent heat. Safety precautions and insulation are essential for accurate results. Final summary. Let's finish with the key ideas. Latent heat is energy absorbed or released during a change of state without a temperature change. Temperature remains constant during melting and boiling because energy breaks bonds instead of increasing particle speed. We use Q equals ml for phase changes and Q equals mc delta T when temperature changes. These ideas explain everyday experiences like sweating, weather patterns, and cooking.